these after school lectures. Really interesting area that we're going to be looking at today, which is we've got a researcher here. This is David, who's a PhD researcher at Imperial College in London. And he very specifically is researching seismology and earthquakes, and he'll go into some of the more kind of the technicalities around exactly what he's researching and the remits and kind of uses for that. We've also got some other guests here who are from Imperial College, from the international office there. They'll also be looking at some of the kind of the broader undergraduate access to some of these areas of study, which come under subjects like geology, geophysics, earth and planetary sciences. There's a kind of a small suite of courses for which seismology is something that ultimately comes out of. So if you've got, as always, any questions for David, particularly about his research and what he's doing, and if you've got further interest in that, got any questions at all about these courses at undergraduate level and looking at that, entry requirements or anything technical at all, or just simply what you'll be studying, and indeed, even if you've just got broader questions about Imperial as well, that's absolutely fine. And we've got three brilliant visitors who will be able to help you with that. So once again, a reminder to please put any questions in the chat, and I'll put that to our guests once we finish the talk. But for now, I'm going to hand over to David, and he is going to talk to you a bit about his seismology research. So David.
Hello, everyone. Nice to meet you all. Thank you, Joe, for your introduction. As he said, I'm David. I'm from Colombia. I'm a PhD student. My background is I'm a geologist. I did my undergrad in Colombia, and now I'm in London. Today is snowing, so it's a little bit cold here, but it's okay. Okay, so my research, I'm working with chondrites. Those are deep marine deposits. And we are going to use some of the tools that we're going to talk later. So as you can see from images, we are going to use seismic data. We are studying something to see with the marine currents and the deposits. And also, I have a job back in Colombia. I work for the oil industry, and sometimes I have to go to drill ships and be there for a month, drilling and describing the course. So it's quite interesting. But for today's talk, my research is trying to look or to find chondrites. So to understand the evolution of deep marine currents. For this specific, I need to know how the rocks are beneath our feet. Yeah, and we need to know the history and how they form. So we do this through a technique that is called seismic imaging, which is what our workshop will be today. Okay, what do we want for you to check today? To understand why we want to image the subsurface and who benefits from this information. To understand that the Earth is made of many layers of rocks with thicknesses of from meters to kilometers. Also to understand how we use seismic waves to image layers of rock in the subsurface. To know what is meant by seismic velocity, seismic reflection, and acoustic impedance, and also to be able to interpret seismic reflection data and pick out structures such as faults. Okay. So seismic data is imaging the rocks in the subsurface. We are going to use P and S waves, but don't worry, we are going to talk about this a bit later. So there are lots of different reasons why we would want to do this to different depths. So from this upper part, we're going to use it in mining. We're using the archaeologists using, but they just use the subsurface 10 meters deep data. Also, the scientists use to study the deep earth interior, plate boundaries, so we can image kilometers down there to find oil and gas, as I was telling you, to understand and try to predict when we may have earthquakes. Also, in order to make safe building and infrastructural decisions, also to find places where to store CO2 or radioactive waste underground, to model underground aquifers and water storage, and also to understand the earth beneath our feet. Okay. So, but what do I mean when I say imaging the rocks in the subsurface? Okay, in the background, what you can see here in the slide is a seismic line. Imagine that you took a slice of the earth and you were looking at the cross section, right? If you struggle to visualize that, imagine that the surface of the earth is like the top of a layer sponge cake. Yeah, so you cannot see the layers when you are standing on the cake surface. But if I slice the cake vertically in half and look, the what you can see is this, right? So this is now how we look the seismic data. Is this a cross section of the earth with imaging that can extend from shallow as a few kilometers, and then we can image that. The lines that we see here are the limits between different rock layers, and these are the limits that we see here in the seismic, like, okay? But let's put these layers into context. You might be thinking of these layers of the earth as we know as a core, a mantle that is a semi-molten mass of rock, and the solid crust. We know these layers exist by using seismic imaging techniques. However, in this session, we are focusing on layers on the earth as much smaller scale. So we're going to focus on this upper part, on the crust. The earth crust is the solid outer shell of the earth and can be up to 50 kilometers thick, but typically between 5 to 10 kilometers under the ocean in here. And when you have mountain ranges, it can be from 30 to 50, okay? But it's not the same type of rock from the surface to the mantle. It's not like that. It's more like this. So we have different kind of rocks, we have mixture of rocks, and it will be depend on the environment or on which the rock was deposited. These layers reflect the composition of the rock, and most of you come across that we have different kind of rocks. We have igneous rock that come from volcanic environments. We have metamorphic rocks that they are come from heat and pressure environments. And also we have sedimentary rocks that they come from erosion, deposition of material in different places, okay? Okay, so, but what does this look in practice? So take a look on this image. Do you know where is this image come from? Can anyone tell me?
You're allowed to turn on your microphones and speak if you want to contribute to the conversation.
Okay, this comes from the Grand Canyon in USA. So can you see these horizontal lines here? Okay, this is a strata. So this is what we use for seismic interpretation. So a rock unit is called a strata when we can see different rock layers, yeah? Because there is compositional difference between one and another. Size image allow us to interpret rock layers in the subsurface because of these compositional differences. So pick these changes in here can tell us how it is made of the rock there, okay? So this Grand Canyon image is great for showing simple rock layers. There is a fundamental and physical law that is called the law of the horizontal, meaning that sediments under the force of gravity will form from horizontal layers like rocks that you can see in the image. However, Earth is constantly in motion because of the tectonic plates. So you see some places in which the crust are going below the other. So we have subducting plates, and then we are going to form different kind of structure here in the Range Mountains. And also you have places where you are originating material. So even though you see that in some places there is like the surface is like horizontal or almost no structures there, maybe you have structures there. So in this case, what we are seeing is that you have different shapes. So this is a representation. This is a drawing that is representing these kind of shapes. Okay. But what we need to understand here. Okay, so we are going to have different shapes, and in this case, you have this structure that have a shape of an N, this is called an anticline. And when you have U shapes, it's going to be called a syncline. Sometimes you have different structures. This is a syncline, but you can see that it has different angles, different deep angles. So this means that they are going or went under different stresses. In some places, you can see faults, and then you can understand why or where the earthquakes are going to happen. You can see a person, so you can imagine how big is this fault. And later we're going to explain that, but think that this is also this one, okay? So maybe if you have some plasticine, we can like shape or what we think that is the shape of the Earth. So in the first thing you have plastic that is different colors, and they are going to represent different composition. And if you like press these ones, you are going to have these, like I told you, these N shapes that are going to be called anticlines, and these are going to be called synclines. And if you put stress in the opposite direction, what you are going to see is this kind of faults, okay? So basically, what we are going to see is that this plasticine is going to represent the composition of the Earth, okay? So, to recap, we know that the Earth is made of different layers, and that these layers are represent different type of rocks, okay? But how do we imagine this kind of rocks? So do you have any questions at the moment? Something that is not clear? We know that layers are different. We have different kind of rocks. We are talking about plate tectonics. So we have many concepts here. And I don't know if you have questions, please just ask. Okay. So we are going to talk something about natural versus artificial seismology. So there are two types of seismology, natural and artificial, as I was telling you. Natural seismology refers to seismic waves that are generated by a non-man-made event and can be induced by plate movements, landslides, and volcanic eruptions. While artificial seismology refers to seismic waves that are generated by a man-made source and can be made by dynamite, vibroseis, and air guns. Okay, so the seismic waves are produced from these sources are going to be the same, are going to be the P waves, so the primary, and the secondary waves. Okay, we're going to discuss a bit more about this. So what is the difference? The amplitude and the frequency that will be varied in different events. And also, if you are talking about natural versus artificial, they are going to have different kind of frequency. So in this case, we are going to call the natural seismology as passive, and active is if it's man-made. So we are going to talk about active source seismicity in this workshop. Okay, so on land, or where we are located, we are going to use different kind of sources. We're going to use dynamite, we're going to use quarry blast, or vibrosite trucks with pistons that hit the ground and generate speed waves. Nowadays, because of environmental restrictions, the more used source of P waves is going to be the vibrosites, because they are not going to generate any damage on the surface. If we're going to talk about offshore, and by offshore I mean in the sea, we're going to have two type of different tools. If we are going to try to find low frequency sources, we're going to have air guns and water guns. And what I mean with low frequency sources, that we have very small frequency, but we are going to cover deep up to tens of kilometers. But if we're going to have an image of the subsurface, of the near subsurface, we can use sparklers. We're going to use boomers, shear profiles, and pingers. So these are going to vary from tens of meters up to 2 kilometers. If you are going to have a survey of a big area, what you want to use is air guns and water guns. Okay. Okay. So let's take a look of behind the artificial seismology or active source seismology. So you may be familiar with bats, right? And their use of echolocation to navigate. The bat emit a sound wave, yeah, this yellow one, which travel through the air. And when it hits an object, in this case, the foot, some of the sound waves is bounce back, yeah? So the bat will determine the exact position of that foot, let's say in this case. So seismic imaging relies on a similar technique, okay? Okay, in this case, like a bat, we produce a wave of energy at the source. This will be our source. Seismic waves are generated by emitting elastic strain energy from a seismic source that I was telling you, an explosion of an earthquake. So this will be our source here. And this can happen by firing out a compressed air when shooting seismic surveys, or water by making impact vibrations as a dynamic explosion. So the waves are going to travel in a radially shape from the source, and then are going to have, but we're going to use paths as a straight lines. So we generate the blast in here, and then we're going to have a rate of energy going to travel. Once it hit a limit between two rocks, some of that energy is going to bounce to the surface. Yeah. So let's imagine that we have several rays, and we are going to have the same rays traveling to surface, okay? In surface, we have something that is called hydrophones. These hydrophones are going to record the information, and we're going to record many, many shots, and then we're going to have something like this, okay? I have a question here, sorry. Sorry, I haven't seen this, so I'm going to come back to here. Are there differences in the structure of the air in different place boundaries? Yes, but it's not related to the limit of countries, because these are political divisions. So we as geologists have like units that are called basins. So basins can be as big as a whole country, or as a whole continent. For instance, our basins today are going to be like the Pacific Ocean that you can see that is a huge basin. But we're going to have some local differences, okay? So this is not related to countries, but is related to sinks or to holes, or as we call basins for deposition, okay? Thank you, sorry for that response. Okay, so seismic waves are generated by emitting elastic strain from a seismic source, as I was telling you, and the waves of elastic strain energy can travel radially, okay? So what we are going to have here is, sorry. So we have two types of waves, okay? We have P waves and S waves. We're going to see an example of this, okay? So we use P waves in active source seismic imaging, and they are going to propagate by compression and dilation of the direction of travel. So as you can see from here, you have some of movement here, and then that's the way the P waves are going to move. In passive imaging, that is really how you look really into deep, you are going to use S waves, because these waves are going to propagate by pure shear. So it's going to be a direction perpendicular of the direction of travel of the wave. So you see this kind of movement. In order to understand more of this, we're going to see this video here. Okay, so we're going to see it now. So first, 1 second, please. Okay. So first, we're going to see the P wave. Okay, as you can see, the wave is going to propagate in the same direction of the moon. Now, we are going to see S wave. You see, this is perpendicular to the sun. We are going to see it again for you to understand better. Okay, so this is going to be the P wave, you see, in the same direction. And now we're going to see the waves that are going to be perpendicular to those. Okay, the first slinky motion shows compression and dilation in the direction of travel of the P wave. Okay, the second is going to show how they move in via shear. Okay. Okay, but we're going to talk now about seismic velocity. Seismic velocity is going to give us information about how the waves travel through the rocks. Okay. So a seismic wave will travel through each type of rock type at different velocities. So we are going to see here. So do you see how the arrows are going to move in a different velocity? This is how it happens actually. So take a look on this, and in different type of rocks, the velocity is going to be different. And in order to calculate this, what are we going to use? We are going to use the density of the rock. We're going to check how resistant the rock is to compression. And we need to check also how resistant the rock is to twist or to shear. So we care about seismic velocity. Without this change in seismic velocities between rocks, we are not going to be able to see any energy bounce back to the surface, okay? So in this case, since we have two different type of rocks, we are going to have that at the limit, we are going to have some energy coming back to the surface. Is this reflection of energy that is received at the surface? And this allows us to see the rock layers, okay? Okay, I think that you have some Excel files, so we can calculate some seismic velocities. I know that this equation might look like it's like complicated, but no worries. We are going to provide you some data. We're going to provide the bulk modulus, the shear modulus, also the densities of the rocks that you are going to look at. Okay, density, bulk modulus, and shear are in the table that you have in the activity 2. And all you need to do is to put those values and calculate, okay? So in this equation, what we need to know is P, that is the velocity of the P wave, the density of a medium. You need to know the bulk modulus or the compressibility and the shear modulus, okay? So we are going to do an exercise. So we have sandstone. Sandstone is a sedimentary rock and is made of a grain size of quartz. So the density range of the sedimentary rocks of the sandstone is going to be between 2.2 and 2.8. The density is going to be 245. The bulk modulus is 20. The shear modulus is going to be 12. So if you have your calculator or your computer, so can you please tell me what is the velocity, the P velocity for the waves in this case, for the sandstone? So basically what we do is to replace the numbers and then we can calculate what is the result for this. Can someone tell me what is the result for sand?
Everyone, that's if you find it easier to say it, do. If it's easier to add to the chat, add it to the chat. Either is fine. If you're, but any good goes at the numbers, that'd be great to hear.
I think all your students are shy today.
Oh, you've got one in the chat there. So we've got 5.71. How does that strike you, David?
I think that is a bit high. So you need to be careful with your calculations. Sometimes it's just the way you do. Remember that first you need to do multiplications, the divisions, and the exactly. Lian has the right answer. 391. Thank you, Lian. Okay, now in your sheet, you have different kind of rocks. So you have sandstone, that is a sedimentary rock. We have basalt, that is a solidified lava from a volcano. We have limestone, that is also sedimentary, but is made of carbonate. We have mudstone, that is made of mud. So these three here are sedimentary. This is volcanic, and this is also volcanic. So with the exercise there, so what do you think? What is going to have the, oh, sorry. So you already see the answer, okay. So which rock type has the fastest seismic velocity? Mudstone, granite, or sandstone? I know that you already see the answer, but from the exercise that we provide you, you can see that volcanic rocks are going to have very high speeds, okay, because of the composition, because of the structure. So as you can see this, we can continue because the answer for this one is granite, okay? So the fastest between these three ones, these three kind of rocks is going to be the granite, okay, because of composition. So guys, tell me, how are you doing? Are you doing okay? Do you want to stretch your legs for a minute or so? Or do you want to continue? Hello?
Sure, we can keep going.
Okay, okay, we can do that. Okay, so you have successfully worked out the speeds that seismic waves will travel through different rock types in the subsurface. So now let's take a look of what else we can learn from these seismic images, okay? How, in this case, how we're going to solve how bright is my reflection. Once we have the data, we want to process it so that we can understand what is happening in the subsurface. We know that different rock types have different seismic velocities from our previous calculations. This is also has an impact of the brightness of our reflections. Some of them, some of them are going to be really bright, like these ones in the upper part. Some of them are going to be really faded, as the ones we have here. But why do we get different levels of brightness? So this is due to a concept that is called acoustic impedance. This will be telling us differences between the two rock layers, okay? Okay, once the brightest lines represent the greatest amount of energy being bounced back into our receiver, okay? So the amount of energy that is going to be reflected is going to affect how we see this, okay? So the amount of energy that is back when the seismic wave bounces is going to be relying on acoustic impedance constant. And this is related to changes in density between two rock types, density 1 and density 2, and also differences in velocity, okay? So this relationship between densities and velocities are going to let us know about the acoustic impedance in the media. In this case, rock types with very different seismic velocities and densities will bounce a lot of energy back to the surface. In this case, you see, this is the amount of energy that we sent to the subsurface. And then we have this bounce back. It's going to be less than the original, but it's going to be a big amount, okay? And but if you have very similar kind of rocks, what you are going to have is you send this amount of energy, and then you are going to have this less energy. So that's why you have brightest reflections when you have more reflected energy, and you are going to have faded ones when you have more similar kind of rocks. So the relationship between this seismic velocity of a wave and density are going to provide us something that we call acoustic impedance, okay? Now we're going to talk what happened or what is going to tell us if they are in different position. So for instance, in this case, if the wave slows down from one rock layer to another, we call this as a negative reflection, and we can use it as a blue line, okay? If the wave moves up or speeds up from one rock to other, we are going to call positive reflection, and it's going to process as a red line, okay? So in order to calculate the reflection coefficient, we're going to use our acoustic impedance, that is density times velocity, and we're going to use our acoustic impedance constant, that is using both densities and both velocities, okay? In the first step, we're going to use the density and the velocity of unit 2 times, and then we're going to do do like a rest here, and we're going to take out the density and velocity of unit 1. Then we're going to divide these from adding the same values, okay? This is going to provide you the reflection coefficient. So acoustic impedance is, again, for you to be clear, is density times velocity of a wave through a rock layer. Acoustic impedance constant is different in rock density and velocity wave velocity between two rock layers. The reflection coefficients give us the values of the acoustic impedance constant contrast between two rock, okay? So I know that might just sound like a lot of letters or words or concepts. So think about what this could mean in practice. Do you think that the reflection coefficients would be greater between the image that we have here that is mainly made of sandstones, or in here that we have a mixture of claystone and shales? So what do you think? Where are we going to have the biggest reflection coefficient? In here that we have similar rocks, or in here that we have different kind of rocks? We have claystone and shales. So what do you think? Where is going to be higher the reflection coefficient? India, correct. So in this one, why? Because we have different rock types there. Okay, so you can go to activity 3, and you have a comparison there, and you can work out the reflection coefficients for different rock types. How bright will be each reflection be? So if you want, you can go through that. And if you want, we can continue. You can check that, or do you have any questions about that? Have you take a look of the spreadsheet? So for instance, if I ask, which pile of rocks has the greatest reflection coefficient across the boundary? The relationship between limestone and sandstone, granite and sandstone, mudstone and sandstone, mudstone and limestone, granite and basalt. So in this case, the different they are, the higher we are going to have the differentiation. So in this case, the relationship between mudstone and limestone are going to have the highest, and also are going to produce the brightest reflector. Okay, this is really important for us, because just using seismic data, using these kind of tools like acoustic impedance and reflection coefficient, we're going to know more or less which kind of rocks we are dealing with. Okay, and these are going to provide us information of where on the basin are we located. Okay, so but why are they important? So Any changes in rock types means change in acoustic impedance, okay? So we have this. The bigger the change in acoustic impedance, the brighter the reflection, okay? So this means that we can image changes in rock types in the subsurface, which allow us to see things like this. Remember that I showed you this image before? This is a fault here. And with those changes, using seismic lines, we're going to be able to see that here we have some faulting, okay? So in the next slide, I will show you an image. I would like you to check it and try to visualize what we just see here, okay? Okay. So think about the outcrop that we just looked and take a look on these seismic images. Look at the reflections. Take a look on the brightest ones. They are not always continuous, are they? The offset between the bright reflections can be used to show that rocks have been faulted. Do you see any faults in here? I hope so. Okay, in this case, what we're going to see is that we have some of the brighter reflections are going to end up to this point. So this is telling us something. Something is going on there. Okay, so what we do is we are going to going to compare, and we say that this reflection is this one, and this yellow is this one. So from the previous image, you have that we have faults here, okay? And this is going to tell us more about where are we located in the basin. Are we dealing with sedimentary igneous metamorphic rocks? It's going to provide us an idea, okay? So in this case, for example, in this first image, we have salt diapers. So the salt was went under really high pressure, and then it breaks its ways and is going upwards. So as you can see, the salt broke these rocks, and you see that it gives shape to the basin. Okay, so we can see this from seismic information, because what you are going to see is some reflections that are going to be cut here, and then you can determine that this is salt. Also, we can see ancient volcanoes. In this case, this is an old magma chamber, and you see how the reflections are showing us that something was happening here, okay? And remember that if this was hot was during a long period of time, it's going to break everything in here. Also, something that you can see from seismic images is this. This is like the scar of an old meteorite impact, and similar as the one that killed all the dinosaurs. So you see here some structures, and you see that here we have major faults in here. So these tell us that something happened there. And we use seismic information to try to interpret these kind of things. So remember what I showed you what I'm doing? I'm doing sedimentology, and I'm using this information to interpret how the basin evolved. But you can you can visit and try to find if there are faults there, if you have volcanoes there, if you have deep impacts there. But also, we can use this to try to reconstruct the geological story of the place. Okay? We cannot see just faults. We can see many things. So we can see this. You have here like a channel of a river, and you have, this is the subsection, we have the depth, and you have some stream velocities there. In the image, what you have is this kind of reflections. So you see that we have a surface here, and we can interpret these images, and then we come from this model, and the original image was this. So from the seismic information, what we have is these horizons here, these reflections here, and we can go back. Then this is our original model. This is what we have, and this is the explanation. So what we do is that we have this nowadays, and we can use seismic to interpret ancient environments. So you can use, we use the sentence that the past is the key of the present, or the present is the key of the past. Okay. What was the difference between the continuous and collaborative reflectors? Okay, so remember that that I told you that the more difference you have, you are going to provide, you are going to have more energy in surface. Okay, so when you have continuous layers, it means that you have a good contrast between these kind of rocks, and then you are going to have more energy on surface, and that's why you are going to see this energy. And in those low energy packages, you are going to lose most of energy because they are pretty similar. So maybe in some places, you are going to have a presence of faults, presence of salt, and this is going to affect the information that you're seeing in surface, okay? We're going to see some examples later and we can discuss that. Okay, for instance, we are also able to see gaps, okay? In this case, you see that in this lower part of the image, you have some reflections going in this direction, yeah? And then you have in this upper part, the reflections are going in the opposite direction, and you have low and high energy here. But what we see here is something that is going this way, right? So this surface is called an unconformity, yeah? And you can see best when the rocks beneath in the surface are orientated in a different shape, yes? So what we are seeing here is that you have in this lower part, they are dipping towards the right, and these ones are dipping towards the left. So it's going to be much easier to see. And in here, as you can see, we have two different rocks here, deposits here. So we have, these have a big, higher angle than this one. So we have another unconformity in this upper part, okay? Something that is important is that unconformities are going to have high reflections. Why? Because you are changing from this type of rock to this one. So this limit is going to show you that something is happening there, as similar as is happening here, okay? Okay, what else can we see? Sediments building up. So think of where the land meets the sea, okay? We have this limit in here. The sediment is transported by rivers to the sea by streams coming from mountains, okay? And we are going to deposit them in a clinophore shape in here, as you can see. So if the sea level rises, then the river channel will be pushed back inland, closer to the river source, and is going to create a new shelf where the deposits material are going to have place to be deposited. But if the sea level falls, so in this direction, so the underlying sediment will have deposit material and is going to be far away from the river source, okay? This means that we get these seismodal shapes that we can see here, okay? In this case, we have that the ocean, the sea was here, and then it moves back. So we have this kind of sigmoidal shapes. And this is going to tell you that the sea level went down with time, okay? So something that we can see from this image is something like this. So we have the original surface was here, okay? But in time 2, we have this new deposit. And in time 3, we have this deposit in here. And in time 4, we have this deposit in here. remember that the sea level was here like long time ago, and it changes because of we have a degeneration of mountains, we have plates colliding, or maybe we have a general increase of the sea level. This is quite complicated. So we have many students doing PhDs on clinoforms. All I want you to take from this is that we can look at changing sea level, but looking at these sediment packages, which means that we can do things like predict how sea level rise with climate change and how are going to affect the land masses. Okay, so now is your turn, guys. So go to the activity 4, and you are going to see 3 different sections for you to interpret. Use your newfound knowledge that I hope you are taking from me of reflection data to pick at some bright reflectors, try some across the whole section. Look for any offsetting. Maybe you are going to have some fault in there. Do you see any obvious unconformities? So we're going to go through these ones together, okay? So I'm going to give you some minutes for you to check. And if you want to open your mix and talk and tell me, okay, I'm seeing this, or I'm not seeing anything, that is okay. Because remember, it's not easy, but the more you pay attention to the structures, the more you are going to see. Okay. So anyone wants to take a look on this? So please, in this one, check if you have some strong reflectors, or if you have some cuttings, some offsets, some different surfaces there. Okay, I'm going to do it with you guys. So in this first one, you see some discontinuities in here. Okay. Were you able to see these kind of discontinuities? Okay, I don't know if I can, I'm able to change color. Okay. Also, in this case, you can follow this and also follow this and also follow this in here and follow this, follow this. See? Okay. So if you continue work with that, you are going to have this kind of result. In here, you see some strong reflectors, and you have some of the faults here. And here in this orange horizon, you see that the fault is gone, right? And you see some faulting in here. And something that we can do is try to put an order or these structures. So what was the youngest? What is the youngest? What is the oldest? So we can discover all of this using seismic interpretation. Okay, so we are now going to move up to the next section. As you can see, this is offshore or in sea seismic information. Okay. What do you see here, guys? In here, we can see some faulting in here because it's cutting, but you see that they are not cutting in this upper pipe, right? But in here, you have the, oh, sorry. In this one, you see this discontinuity here and this in here. You see some here, 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 here. Okay, and also you see something that we just saw. Here you have this surface, and here you have this surface. So this means that the sea long time ago was in here, now then was here, and now is here. So what you see is how the continent was moving towards the sea, right? So that's something that we can take from this from this information. Also, we have here some unconformities because look, this has a different shape, and we have another shape here. You have this one, and you are going to have different kind of interpretation. So in previous ones, the main thing was the faulting. In here, even though we have faulting, the main thing to understand here is sedimentology. And in this one we saw an example for this one in the presentation. So in these ones, what we are going to see is that we have this surface here. And remember something, you are going to have as many interpretations as geologists are, but what you need to do is try to respect or honor the data, okay? So here we have these kind of shapes. Also, we see how this is being broken, right? So we have this deposit, and we might say that this one is this similar. It's going to continue to the whole basin, okay? So we are going to have this. So you see, we can see many things using seismic. We can see salt, we can see faults, we can see different type of rocks, we can see how the environment evolved. In my case, we're going to see how, remember that long time ago, Australia was tied to Antarctica. So they start splitting apart. So now we can understand how fast and how they are moving compared to each other by describing the deposits in there. So it's using this seismic information, and this data is really, really, really useful to understand how the Earth is evolving, how previous events behave will tell us maybe how we're going to behave in the future. Okay, so thank you so much. Thank you for your time. I know there is a lot of information that I provide you. It's really big things that you can do with this kind of information. And if you have questions or anything, just please ask. Also, you have some additional pages there, additional sites, so you can check. You can type your questions if you have more questions about this in the future. And then that's it, guys.
Listen, David, that was absolutely fantastic. I think, you know, when we're talking about getting in researchers from places like Imperial, that's what we want, you know, that level of depth, that level of interest in someone's research. That's fantastic. And with the interactive elements as well. You have spoken for a long time. It was brilliant, but it is quite a long time. So we're coming near the end of the session. I did just think then, I'll maybe just give you a slight break in here. I'll maybe, if there's time, we've got about 5 minutes, and I'll maybe do come back to you with a couple of questions. I just thought actually it might be worth just bringing Victoria in. Is she still there? Victoria, are you around? Oh, yeah. Just, I did mention it, didn't I, briefly at the start, in terms of the undergraduate courses that would lead to doing the kind of research that that David does. So from our students' point of view, what that pathway might look like, and then you can maybe give a bit of information there. And so what's it likely? What are the courses, and what, just a little bit of information about the undergraduate end of this?
Yeah, so our undergraduate students come to us with a few science subjects. So to study with us, you will need 2 science subjects for geology. If you want to do earth and planetary sciences, one of those has to be maths. And if you want to do geophysics, those two science subjects have to include maths and physics. And the reason for that is when you get into the department, you are using all of the sciences, from computational science, maths, physics, chemistry and biology, if you're doing paleontology, to pull that together and understand the systems and processes that shape the Earth and other planets. And from there, there's lots of applied things that you can do, but really understanding how our planets work is what we do in our department, and bring together all of those sciences. So some of the things that people do in the department is chemistry. They certainly look at seismic data and interpret it, as David has taught us this morning. And when it's not a global pandemic, we the geologists get out into the field and see these real life applications of what they've been learning in the classroom too.
Fantastic. That's really good. And just before I move back to David, just to ask him about his kind of routine and what he's done, what are some of the other, obviously that's one very specific route, the academic route, and into that area. What are some of the other areas that students from these disciplines are going off into, Victoria? What sort of industries and places are they ended up?
Well, the people who are doing earth science degrees are really numerate, so you become good at maths, often in a very applied way, which can lead you into lots of different careers. And one example that lots of Imperial graduates from our department go into is working in the city in finance. Geoscientists, earth scientists are good at making decisions with limited information. As you can sort of see from David's talk, that's a super transferable skill. People go into things like risk and insurance with that sort of ability to bring together their data knowledge and apply it to a real life situation, even if it's not a geological situation. And there's lots of teamwork in earth science as well. So you'll be sometimes out there in the field or working on coding a program together. And so we find that students have a range of skills that let them do those applied jobs, like being an environmental scientist, for example, like working in areas of sustainability, perhaps, like using their maths and data interpretation skills to understand data on other planets. For example, working for an organisation called the now I've forgotten the name of it, in Earth observation. And so it's a real range of things that can be earth science applied jobs, working as a geologist in the field, but can also be a lot broader than that.
That's fantastic. I'll just move back over to David then very quickly and just say, David, do you just want to, a lot of people often ask me, obviously, as a kind of looking at careers and actually looking at becoming an academic and going that way into it. And obviously you're in a very particular field. Can you just give a little bit of an outline maybe of just what your background was and how you've come into this particular area?
Okay, I started as a field geologist. So when I got my undergrad degree, I went and I did maps, I did mapping. So I went to different outcrops and take a look on the samples and then trace maps. After that, I joined the oil industry, but I always related to onshore operations. But like 10 years ago, I started working for the national company in Colombia. And now we are very interested in offshore, because offshore is not just to provide new resources, but knowing the offshore will tell you how the earth is growing and how it's changing. So I really into that and see how things evolve, how our earth is changing and how we change the earth, because the marine currents are going to be always there and we are going to be affected by them. So understanding them, we are going to see how we can work with them to help us instead of affecting us, okay? So that's why I'm trying to be involved in this kind of research about contracts.
Fantastic. And just to, I normally ask something about the future, really. Again, obviously a lot of our students, by the time they are you, obviously will be a long way in the future. So what do you see over this next 10, 15 years? What do you see as the main sort of areas for development in your research? What are the big challenges ahead for us?
Okay, so as you know, we all are moving to new energies, right? So geology is really into that too. Even though we are going to still using oil fuels or fossil fuels for, I don't know, maybe 20, 30 years, we need to move together as a energetic change. So geologists are good for that because we can try to find where we have, like in Iceland, that we have a geothermal energy. This can be more for the future. Also, we are trying to find, we have CO2 problems, so we need to find where to storage them. And Imperial is going in that direction to try to find like for geologists to try to find where to storage the CO2. Also, I think that we are going to need more water. So if we have groundwater, we can try to understand where are they located, and we can extract water for our usage. Also, since we are growing in population, yeah, so we need to find the best places for to live, because nowadays you see that we are being affected by natural disasters, and the natural disasters have been happening all the whole time, yeah. But what happened is that we as humankind are living in not good places. So if you you always need to have a geologist, yeah, because they will tell you, okay, this happened long time ago and it may happen again. So if you know the history, that might work and help you, okay?
Fantastic. Thank you, David. We're coming to the end now. Just like to thank you very much for coming. Really appreciate it.
Thank you so much. Thank you for your time. Thank you for your attention, your questions. It was a very lovely experience. Thank you.
Lovely, beautiful finish there. And thank you, Victoria and Jen as well, for coming onto the call. As always, we'll just remain on the call for another couple of minutes in case you have any questions you want to ask verbally. But if otherwise, I'd like to wish you all good evening, and please do switch yourself off from the Zoom call. Thank you very much for coming.
Thank you. Bye-bye.